Hello, my name is Josh, and today I'm going to be discussing a fidget spinner. This is actually more than just a fidget spinner. It's a planetary gear system, which I designed entirely myself. And by the way, you can find all of the files for this on Thingiverse. It is actually an OpenSCAD model, so you can also take a look at the code that I have written, including the code which generates spur gears. Specifically, what I want to go over is what is a planetary gear system, and what are some of the design considerations that you have to take into account when making one of these things. So a planetary gear system is an assembly of gears, which has a sun gear, which is this black one, surrounded by one or more planets on the outside, affixed by an arm that connects everything together. And what makes it pretty interesting is if you were to fix the arm and rotate the gears, they would all rotate like a normal gear assembly. If you were to instead fix the sun and rotate the assembly, it can rotate around the sun. The planets rotate around the sun, which is pretty cool. It has it has a whole bunch of other features, but one really other cool one that I have here ready to demonstrate is if you were to take an internal gear, which is one of these things, it's kind of like a spur gear, except all of the teeth face inwards. Provided it is the right amount of teeth and distance and everything, you can actually create an assembly like so, which has the planetary gear system rotating around the ring. Or conversely, you can rotate the ring around the planetary gear system. It's a very powerful mechanism, which I will talk about more in future videos. But today, we're just going to be discussing the nuances of this fidget spinner and some of the design considerations that went into creating it. The first design consideration that I want to discuss is how do you actually attach the gear to the arm? So this is an example of the arm assembly. It is a piece which looks like this. It has 3 holes for the planetary gears, a space for a bearing, and then the sun gear will go there. So how do you actually attach a gear to something like this? And in this particular design, I use something called the capture nut, which is where the holes here have a hexagonal shaped hole, which exactly matches that of a nut. So if I were to put the nut inside of this capture nut spot and push hard, you can see it perfectly fits in there. And what does this allow us to do? Well, a capture nut will allow us to thread a bolt through the part. Once it got to the end of the thread, the pressure of the bolt against the part would pull the nut and recess it fully into the part. This creates a very tight bond between 2 different parts. So we have this gear and we have this part. And if I wanted to attach both of them together, I would simply put the bolt through the gear and then I would attach it. We have it affixed. Now, the very first problem that you're going to run into is the fact that although it is very strong and affixed, I cannot very much rotate this gear easily. It has no movement because it's too tight. This has to do with how bearings work. You have to make sure that the inner ring and the outer ring are not fixed to each other. So that brings us to design consideration number 2. How do we make it such that the bearing can move freely? And I created these. They take about 2 minutes, I think, to print. They're very fast. All they are is a spacer. So if you were to take this spacer and put it over the bolt, I'll push this close so you can see. The spacer, it's kind of hard to tell, but the spacer is only touching the innermost concentric part of the bearing. And this will allow the bearing to actually move freely now. So if I were to put that spacer on, but this time, with the power of the spacer, it can rotate freely. And that is pretty much all I did for making sure that everything could rotate. Now let's talk about design consideration number 2. Although we have this gear and it can rotate freely and it is attached to the arm, it has one somewhat major design flaw. Because it is using a pressure fit mechanism to hold the bearing in place and my tolerances aren't that great, the worst part is if I just pull with not even really that much force, I can bring the whole thing apart, and that's kind of weird. So that brings us to design consideration number 2. What we have here is called a pressure fit mechanism. So that means that you literally just use pressure to push the piece in place and then it is fit. That kind of works, but the problem is, of course, your tolerances aren't always that great. So I came up with a whole bunch of different possible ways to solve this problem, and only one of them worked. Concept 1. Suppose you had instead a concentric ring which the bearing fits inside of. This way, if no amount of pushing it will push the bearing through that particular dimension. And then you had another concentric ring which the bearing fits on the other side. This was kind of an idea, didn't work. You would take a gear, put the outermost concentric ring inside of it, and then put the bearing inside of that, and then you would have sort of this meshed bearing thing. But that idea failed. Next, I had the concept of take that concentric bearing, but instead of having an interior one in the gear, why don't we build inside of it a lip that will capture it? So this kind of works. It's a step in the right direction. No amount of pushing the bearing will go through one side of the gear, but it kind of has that issue. The idea that ended up being the winner is a gear which has a lip to keep the bearing in place on one side of it, while having a really strict tolerance for press fit on the inside. So you can push this in there, and it's actually very tight. You cannot push the bearing all the way through on one side, and that just leaves this one particular face of the gear which you have to worry about. And if you notice, when I had pushed the gear off of the assembly earlier, the bearing is still in place, which is good for us because that means if we can lock down one side of the gear and know that the bearing isn't going to go the other direction, then we have essentially made a solution that is going to work for our fidget spinner. So that is the final solution that I came up with. A pressure fit bearing, but a lip on one side built into the gear, which prevents it from wiggling too much and ensures that your assembly is going to maintain its stability, no matter how much weird pushing you're doing on it. So where does that bring us? Well, we have 3 planet gears. Each one has a lip on one side and a bearing exposed to the other. Each one uses a spacer, as you can see right here, to ensure that the distance is exactly the same on all sides. From there, we have the arm, which uses the capture nut in order to put and ensure that the planetary gears are safe and secure against the assembly. So we have this. Another interesting aspect of this design is that the arm itself has to have a bearing. So to solve this, I have 2 different caps, one on either side, which sandwiches the bearing together. And they have a strong enough tolerance that it's not going anywhere. I do not ideally enjoy this design. I think I will revisit this shortly. However, it is too difficult to take apart at this point, so I'm just going to roll with it for now. The sun gear gets a bolt. On one side of the bolt, we have a spacer. The bolt goes through. On the other side, we put another spacer. The reason it needs a spacer on both sides is because of this design I was telling you about with the sandwiching. The last thing that I had to make is this nub which is essentially what you hold on to when you do the fidget part of the fidget spinning. And the nub also uses a capture nut, just like everything else. And putting it all together, you have a beautiful fidget spinner.